Let's try a few examples utilizing the work-energy theorem. Here we have a 6 kilogram block that is initially at rest on a surface, and it's going to be pulled to the right by a constant horizontal force of 12 newtons. We of course know that we still have the gravitational pull on this object and a normal force on this object as well. And we're ultimately looking for the speed of the block after it has moved through a displacement of 3 meters. Now, if we attack this problem using work and energy considerations, we can right away note that the force of gravity and the normal force are not going to do any work in this situation. Since the block is being displaced to the right 3 meters, these forces, which are at 90-degree angles from the direction of the displacement, can by definition do zero work on the object. So only the 12 Newton force is actually in the direction of the displacement and therefore can do work on the object. We know that that work is equal to that constant force of 12 newtons times that displacement of 3 meters. Now, to look for the velocity of this object once it has gone through that 3 meter displacement, we can take this amount of work, which the 12 times 3 would give you 36. We can take that amount of work and set it equal to the change in the kinetic energy. Basically what that means is we are setting this equal to a 1/2 mvf squared minus a 1/2 mvi squared. Now this block was initially at rest, meaning that vi was actually equal to 0, making this entire term go out to a 0. We can in fact put in the mass of the block, so I can place that value in there where the m was equal to 6, and vf is now the only variable that we do not know. If you want to take a second to pause the video and solve for yourself, you can solve this equation and find that the final velocity of the block comes out to be about 3.46 meters per second. Notice that in this case, we get to this final velocity fairly easily. We did not have to set a net force equal to ma and then use kinematic equations from there to get to this final velocity. Although that consideration would get us to the same answer, we're finding that this method of getting to that answer is a little bit quicker and a little bit easier. Let's try another problem. In this problem, we have a massless spring that has a spring constant of 1,000 newtons per meter, and it's placed on a table in a vertical position, so the spring is kind of looking like this. And above this spring, we've placed a block that's going to fall onto the spring, and obviously once it falls onto the spring, it's going to begin to compress that spring. In fact, in this problem, we are looking for that maximum distance that the spring actually gets compressed. We know that this block is starting out 1 meter above the height of the initial spring. So this is where we begin our problem. Now, in this case, we are looking at the spring falling on, or the blocks falling onto this spring, and at the point where it is at maximum compression, so maybe the spring ultimately ends up somewhere down here with the block resting on it. We're going to call this distance that it compresses the spring some distance d. And ultimately, that's what we're going to be looking for. So we'll name that variable here. At that point, we know that this block has reached a velocity of 0 because at maximum compression, it's about to change direction and spring back up in this oscillation as it bounces on this spring. And in that point where it has, where it's about to change direction, we know that that velocity is going to have to reach a 0 velocity at that point. So if we were to analyze the total amount of work done on this object, or the net work done on this block, we'd have to consider a couple of things. We have to consider both the gravitational force pulling down on the block, as well as the spring force that would be pushing on the block once it comes in contact with that spring. So in looking at each of those forces, the force from gravity is going to be a constant force of mg, and it's going to act over a distance of the height that it began, which was the 1 meter, plus the distance that it compresses the spring. So we're looking for the total distance that gravity is acting, which was the initial height, plus the compression distance. In looking at what work the spring does on the block, the spring is pushing it in the opposite direction, so we'll put a negative sign on that. And of course, like we said before, springs can exert a force of kx. So when you integrate that force and look at the amount of work done by the spring, it's a 1/2 kx squared. As we now begin to analyze this, we would recognize that this x that we have in our 1/2 kx squared for the amount of work done by the spring is really the distance that the spring gets compressed. So we could replace that x with our d variable that we're looking for in this case. Now, as we look at a few of the values that we can plug into this, we could simplify our expression for net work by plugging in the mass of the object, which was a 1.6 kilogram object, multiplied by our gravity of 9.8. The initial height that it began at was our 1 meter, plus the compression distance that we're looking for, minus the 1/2, our k of 1,000, and again our compression distance that we're looking for squared. As we begin to simplify this a bit, and I'll give you a second if you'd like to pause the video and try to simplify this just a bit, we're going to find that we end up with a quadratic equation. And ultimately, as we look at this quadratic equation, we're finding that I would like to put them in order from the variable being squared. So 1/2 the 1,000 is a negative 500, and the d is being squared there. When I multiply the 1.6 by the 9.8 and then distribute that through to each of these pieces here, I would have a 15.7 multiplied by the d and another 15.7 just multiplied by the 1. Now this is our expression for the total net work done on the object. If we were to analyze this problem in terms of the work energy theorem, we know that this total net work can be set equal to the change in the kinetic energy. In this particular case, the change in the kinetic energy was beginning at rest, where the block was dropped from rest or velocity of 0, and in the end, we know that when it reaches that maximum compression distance, it also has a final velocity of 0. So when we look at the change in the kinetic energy, we have a beginning and ending kinetic energy of 0, or a change of 0. So ultimately, we are just setting this equation equal to 0, and we can now solve this quadratic equation. Go ahead, pause the video, plug it into your calculator, solve for that. What you find is that you get two values of d. You'd find that d could be equal to 0.19 meters, and our second value, when we plug this into the quadratic equation, is a d value of negative 0.16 meters. We want to choose the positive root here for our answer because we did call down the positive direction in leaving the force from gravity doing positive work and the force from the spring doing negative work. We were in that case calling down the positive direction. So it is compressing it in a downward direction about 0.19 meters. If we were to look at what this negative value would mean when we solve for that in the quadratic equation, ultimately this would be looking at what would happen if the block actually stuck to the spring and then began to oscillate up and down over and over again as it were to bounce. Its maximum stretch would be this stretch of about 0.16 meters where the block again comes to rest as it is attached to the spring. In this case, if we're looking for a maximum compression distance, that's where our 0.19 meters is going to come in as our final answer.